Hereby I open the academic ceremony in which Eva Dijkstra will defend the academic thesis, The Heart-Brain Connection, a pathway to personalized TMS treatment. May I invite you to present a summary of your study and the conclusions of your thesis?
Thank you, dear Pro-Rector. I'll start. Dear Pro-Rector, dear members of the Defense Committee, dear supervisors, dear colleagues, family, and friends. Welcome to my presentation. In the next 15 minutes, I will tell you about the research I've conducted in the past few years on this, I think, important connection between brain and heart, and how to use this to improve RTMS treatment for depression. So, what is depression? As most of you probably know, this is a serious and common mental health condition that affects millions of people around the world. And currently, the estimates are that even 1 in every 6 adults suffers from depression at least once in their lifetime. People that are depressed have a low mood, they can feel hopeless, it can affect their sleep and appetite, and in the worst cases, it can lead to suicidal thoughts. And people with depression are 20 times more likely to die by suicide compared to people that are not depressed. So all this information shows us that it's really important to make sure people with depression get timely and effective treatment for these symptoms. And the most commonly used treatments are psychotherapy, so talk therapy, and medication, such as antidepressants. However, about 1 in every 3 people does not respond well to these treatments, and they remain depressed. And it's also known that medication can lead to a range of side effects. So another effective treatment option for depression is brain stimulation. And in my thesis, I focused on a form of non-invasive brain stimulation called repetitive transcranial magnetic stimulation, or RTMS. And during this treatment, a magnetic coil is used to apply small magnetic pulses to a brain area that is important in depression, called the DLPFC, or dorsolateral prefrontal cortex. And it's known that this area is important for mood and emotion. And the effect of TMS comes from not only reaching this DLPFC, but actually rebalancing, or you could say maybe reset a whole brain circuit in the brain that is not functioning well during the depression. And one of the important areas that we want to reach is the subgenual ACC, or SGACC. When the TMS is applied and reach this connection to the SGACC, it's known that this is that it mostly works for the patient. So the TMS, it is very effective, but still also here, not everybody responds to the treatment. And I think the goal of my thesis was to find out whether we can improve this treatment in some way. Can we find out whether some people are, for example, more likely to respond to treatment? So in my thesis, I focused on two questions. The first, who might benefit from RTMS? Are there individual characteristics that make someone more likely to respond? And there we looked at whether sleep disorders next to the depression have any impact. And then in the second part of my thesis, I focused on how to improve RTMS outcome per individual. And can we use heart-brain coupling, which I will explain more in a bit? Can we use that to localize the TMS specifically at a certain area that well, makes someone more likely to respond to the TMS? So we did 3 studies into heart-brain coupling. First, to check whether this technique is feasible and reliable. Then to see if this heart-brain coupling tool is actually connected or shares the brain network of depression. And then finally, I think the most important question was investigated in the final study, where we wanted to know if these findings translate to clinic and whether patients with depression can actually benefit from this method. So to dive into the first topic, sleep disorders. As you already saw at the first slides, people with depression often also have sleep disorders. And it's known that sleep disorders can have an impact on the severity of depression. So they make this depression worse. And in, for example, medication, sometimes the presence of sleep disorders makes the chance of the medication working less. So we wanted to know whether sleep disorders can also impact the likelihood of responding to TMS in patients with depression. So to that end, we included 2 big groups of patients. First, a group of 197 to well, study what we wanted to investigate, and then we included another 102 patients to see if we could replicate the findings from the first group. And in all those patients, we looked at whether they had a sleep disorder before they started treatment, and also which sleep disorder. So you have insomnia and restless leg syndromes. So there are different types of sleep disorders. When we had measured their sleep disorder, we started treatment with RTMS, and after a full course, we determined whether they responded or not responded to treatment. And we thought probably patients that have a sleep disorder have a reduced chance of responding to the TMS, and that could tell us that it might be valuable to first treat the sleep disorder and only then start with RTMS for depression. But surprisingly, we didn't find this. So everybody that received TMS, they all responded likewise. So the sleep disorders did not have any predictive value for the TMS success. We did find that men with insomnia and circadian rhythm sleep disorder, they had a more severe depression overall. So here you see on the y-axis the severity of depression, and over time, this is the course of treatment. The men with insomnia, or the green line, they respond in the same manner as the men without insomnia, but in the end they are still more severe depressed. So these results show us maybe that we could combine a treatment approach so that these patients not only receive the RTMS for depression, but that you would also focus on these insomnia complaints, which maybe would lead to better outcomes overall. So then next, the, I think, bigger topic of my thesis, it's even the title of my thesis, the heart-brain connection. It's known that the brain is connected to the heart through the vagus nerve. And other areas involved are the DLPFC and also the SGACC. among other regions. So this is a simplified version. And when this heart-brain network is activated, you see a parasympathetic activity, which means that the heart rate lowers, you can see a blood pressure decrease, heart rate variability goes up. And this is interesting because, as you might remember from a previous slide, when we stimulate patients with depression, we actually focus on the same brain area. So we want to stimulate the DLPFC. We hope to reach the SGACC during TMS. And apparently these brain areas are both involved in the depression, but also in the heart-brain network. So that makes the case that if the TMS is applied in the right way and you reach this network, you will also activate the vagus nerve and thereby lower the heart rate during TMS. And this is, I think, the whole basis of the next 3 studies. Mostly that if you can use only heart rate to see where you're stimulating on the brain, because apparently at that specific spot you're reaching these brain areas you want to reach, because we know these are more effective for depression, it would be actually a very simple output measure of target engagement. And that's a term to say where exactly do you stimulate in an individual patient. So you could say it's kind of a GPS signal as it's pictured here. Importantly, we didn't only look at heart rate deceleration, because that's also influenced by other things. Just by sitting down, your heart rate would also go down. So we wanted a more reliable biomarker. So we looked at the fluctuations of the heart rate in response to TMS, which is visualized in this image where the yellow bar is the TMS, which goes on and off, and the red line is the heart rate. And during TMS, you see the heart rate slowing, and then when the TMS is off, it fastens again. So then it normalizes, slows, and then normalizes, and then slows. So this response is called heart-brain coupling, which is the biomarker that we wanted to use to see if this can help us improve target engagement. So in chapter 3, we wanted to see whether this biomarker is feasible. Can we actually find this when we stimulate in healthy people in this case? And is it also reliable? So first of all, we stimulated 2 different areas of the DLPFC in these healthy people. 2 different targets in the same brain area, but they are both widely used in clinical practice. And we saw that for some individuals, the yellow spot would be showing the strongest heart-brain coupling. So we could definitely visualize that this was happening in the heart rate. While for others, the pink area would be the better site, if you could call it that. So there was stronger heart-brain coupling, and this seemed to be site-specific. So that means that it's that for the one individual, this might be the better entry to the network in the brain, while for the other, it would be the yellow spot, for example. And then we also wanted to compare sham TMS compared to real TMS. Sham TMS is kind of fake, it's not real stimulation. And we saw that when we used sham TMS, there was no heart-brain coupling in the visual in the heart rate, while with real TMS, the heart-brain coupling was clear. So these first results really showed us that there's something to it, to the heart-brain coupling, that we definitely wanted to investigate further. So that led us to the next study, in which we included brain imaging. Because now we wanted to know, is this depression network and this subgenual ACC area that I've also already mentioned a couple of times very important? Is this actually involved in this whole heart-brain coupling? Because for now, we only have measured the heart rate. So we put healthy people in an fMRI scanner, the brain imaging scanner, and we defined a lot of different areas on the brain that were either connected or not connected to the subgenual ACC. And then we stimulated all those different areas with TMS, and what we expected was that all the targets that would show connectivity to the subgenual ACC would lead to heart-brain coupling, because then we would reach this heart-brain network. But the areas not connected to the subgenual ACC would not show us the same, or at least less. That was the hypothesis. And actually the results that we found were very promising. So we found that indeed, the areas that were connected to the subgenual ACC showed more and stronger heart-brain coupling. And in the graph also, you can see that there's the heart-brain coupling is on the y-axis, and on the bar on the left side, you see the connected areas compared to the other two bar graphs, who are the not connected areas. So this difference was significant and showed us that there's a real connection between the heart-brain coupling tool, you could say, and this depression network that we know of by functional imaging. So these results led us to our final study, in which we wanted to translate findings from our healthy subjects towards patients. So we included 101 depressed patients in the clinic, and we optimized their stimulation site based on heart-brain coupling. And then here we wanted to know whether the strength of heart-brain coupling at that stimulation site, so how much does the heart respond in that specific site, will that make people more, more likely to respond to the treatment? So will it lead to higher response rates? And here we also found preliminary but very promising results. So we measured the response rate after 15 sessions in a full course of treatment that's mostly 25 sessions or more. But at session 15, this is a form of early treatment response. And we saw that patients with heart-brain coupling or strong heart-brain coupling, which is the yellow bar, showed 29% response rates. And the response rate is the height of the bar. And compared to only 11% in patients that only had little or no heart-brain coupling. So that was significant, and also I think it shows that there's something to it. So the heart-brain coupling does predict how well someone will respond. So these results were promising, and of course, a lot more research needs to be done. But at least to summarize what, is I think summarized in my thesis, is that to the question who benefits from RTMS, we found that sleep disorders did not have an impact on the outcome in depression in RTMS, which actually means that people with and without sleep disorders can both benefit from RTMS. So that's also important information. And then to the question how to improve RTMS outcome, and then specifically the localization, we think heart-brain coupling showed this relation to the TMS outcome in our first sample, and that it might be a game changer for personalizing the treatment location in the future. And even though this was a first big study in patients and we need to investigate this further, I'm hopeful that these results will bring us one step closer to better individualized mental health care in the future. So thank you very much for your attention. I'll give the word back to the pro-rector.
Thank you so much for this very clear presentation. And now the opposition will be opened by Professor Bernadette Jansma, Professor for Cognitive Neuroscience of Language Processing at the Department of Cognitive Neuroscience at the Faculty of Psychology and Neuroscience at this university. Bernadette.
Thank you, Pro-Rector. Dear candidate, first of all, let me congratulate you and also your supervisors to this great work. I read it with pleasure, interest, curiosity, and I learned a lot. Very well written, also well published already, and I think it is another test case of teaming up and combining different disciplines under one hat. And you do this in an excellent way. And I think I counted at least four different disciplines like psychiatry, psychology, cognitive neuroscience, but also technology and this advanced type of looking into brain networks. So this also brings me to my question, and it's just like out of my aim to understand this better. And I focus more on chapter 5 now. And you already nicely explained a bit the relation of this HBC, this heart-brain coupling and depression, but still it's sort of at a general level. So I wonder, could you go a bit deeper and share your view on the relation between them? Because you mentioned there's something to it. You see a relation between HBC, responsiveness, and type of depression. You also signaled that it is related to probably sharing neural networks, but could you describe at a more deeper layer how you think these networks are interconnected?
Highly esteemed opponent, thank you for your kind words and for your question. For the part of the networks, we have seen that this frontal vagal pathway, which I just referred to as the heart-brain network, I think more in a more simple term, involves a lot of brain areas besides the ones that I've mentioned. But then it's known that from the DLPFC there's at least connection between also I think the dorsal ACC and some important areas in the brainstem, such as the I think the nuclear solitaris tractus or the NTS, that leads to the vagus nerve, leading to the deceleration of the heart rate. And this this whole network, I think that's important in depression, but in more psychiatric disorders. So it seems to be that this autonomic functioning is a maybe common denominator between different psychiatric symptoms. And then, well, it seems that the DLPFC and subgenual ACC and vagus nerve are also involved in depression specifically, as for example, DBS is focused on the subgenual ACC, the vagus nerve stimulation is effective for depression as well. So that's mostly the background. I hope that starts to answer your question.
That's very clear, and I think it's great to look into this way. So, but I would like to go on to figure 2 now in your chapter 5 on page 88, where you show nicely that actually something happens to which is nice, like the depression score goes down over time across the TMS sessions. But when I look into the red and the blue curve, then actually they go down in the same way. So you have figure 2.
Yeah, I have it in front of me.
You see it?
Yeah.
So how relevant is then this pre-check on the HPC responsiveness? If I would be either the red group or the blue group, I would be equally happy because I improve.
Yeah, no, it's a very valid question. I also think the p-value wasn't even significant here. So I think we mostly included this figure to show a bit that what's happening, and it seems that the group with heart-brain coupling does kind of cross the line, so there's an interaction. But because this is only session 15, we don't know the follow-up after. So it could be that this is the cutoff point where people with the heart-brain coupling would respond even more. But I agree, based on this figure, you would think it might not matter if you have it. But you see in for example, the BDI scores, that there is, I think, significant difference in the, I'm not sure if it's here, but the amount of, so the BDI drops with 11.2 compared to 8.5. So at least that's a start in the first 15 sessions only.
It's a bit deeper, yes. Okay, but fair enough, huh? So I think, but overall it still means TMS works, but the question is whether HPC would add to the improving or tailoring or stratification. But okay, so I have another question. It might be a bit more technical now. I have 1 more minute or 2. Yeah. So that relates to the definition of your HPC marker, where you, and I think you've referred to it at page 84 in your method section. You refer to this 10 Hertz DASH protocol that you use.
Yeah.
And you also described this very nicely by having 5 seconds stimulus, I think at 1 Hertz, and then 11 seconds off. And then in total, you described this as a 1 divided by 16 equals 0.0625 Hertz.
Yeah.
Later on, you describe the same range in power. So therefore, for me, that was relevant. And for me, it was relevant to understand how you would define a non-cyclic protocol into as a cyclic Hertz entity?
That's also a good question. So I think for heart-brain coupling, you need a pattern protocol with TMS because you need this on-off period to make sure the heart rate has time to decelerate during the TMS and also to normalize again. And another important aspect is that you don't want the frequency of the heart-brain coupling to be too close to something else, such as the respiratory sinus arrhythmia. So, for example, we were struggling with that with the ITBS protocol, which is 0.1 hertz, but I think that's already a bit approximating to the RSA. So I think this 0.0625 hertz is a very good protocol to use because you will see something that is not induced by breathing. Nobody breathes that slow, and thereby it's very specific.
Okay, I would have further questions, but I fear my time is up, so I give the word back to the panel. Thanks a lot.
It is. Thanks very much. The opposition will now be continued by Dr. Martin Tick. He has expertise in TMS and fMRI and is affiliated with the Center of Medical Physics and Biomedical Engineering from the Medical University of Vienna in Austria.
Dear Prorector, dear committee, thank you very much for inviting me today and let me join this nice event. Also thank you to the supervisors. Dear candidate, thank you really very much for writing this excellent thesis. I can only congratulate you on this because it's not only exceptionally well written, but it also has the potential to change a neuroscientist's mindset by rewiring the brain to better incorporate the heart. Now to my first question. You nicely introduced the heart-brain coupling factor in chapter 3 of your thesis as a time frequency analysis result of ECG data that was recorded during TMS. And the idea is that the induced current in the brain somehow changes the pathways in a way that you later see those traces in the heart rate. But in its essence, the heart-brain coupling factor is still a very indirect measure of what we are really interested in, which is the direct cortical response. So why should you actually look at the heart response if you could measure the direct cortical response, and what techniques would be out there to do so?
Esteemed opponent, thank you for your very kind words and for your question. And of course, this is a very important question as well. So in terms of functional connectivity, this is a very clear marker of response. So if you have an fMRI scanner available, I think still it's very nice if you can define the functional connectivity and see, make sure a patient receives treatment there. I think mostly the focus of the heart-brain coupling is that an fMRI scanner is not widely available to every clinic that applies TMS. It's expensive. You need personnel that is capable of working with the machine and with the outcome. And the whole point of finding a biomarker such as heart-brain coupling would be to have an approximation of the functional connectivity in the brain by something as simple as heart rate, so that you only have to, measure heart rate. And I think even if that would be a bit less precise as functional connectivity, if it would be widely available because all clinicians can apply it, it would still be, more valuable maybe even in the end than functional connectivity.
Mm-hmm. Because you mentioned availability and also cost was mentioned. Do you think there are specific patient groups or other specific geographical regions or some other scenarios where your heart-brain coupling factor is especially important?
Yeah, so I think at least in Western countries, I think there's still a lot of fMRI scanners available, and especially in academic settings, it's more easy to apply this technique. But in lower income countries, I think it's even more important to include something like this, because I think as most people that use it, also from our clinic at NeuroWave, they can acknowledge that it's not very difficult to get used to this measurement, and also patients tolerate the treatment, the assessment with heart-brain coupling well. So I think it's, it has really potential to be something simple and effective.
Thank you. So you also mentioned in the general discussion in the end, you mentioned that heart-brain coupling could also be a potential tool to come up with a prefrontal threshold, similar to the motor threshold that actually is the intensity needed to see a finger twitch in your finger. But besides that, there are other methods to individualize dosage. For example, people have suggested to use either a depth correction, so they adjust for the different depths in different targets, because you also found like different dose response curves for different cortical sites. So this could be also adjusted by just depth correction or by E-field modeling. But do you think that heart-brain coupling could provide some benefit over those metrics that cannot be explained? So something that cannot be explained by basic biophysical properties, like how the distances vary between coil and target?
Yeah, I think for the, I'm not really an expert on the E-field modeling, I think, but I know you can use it to approximate how the pulse will enter the brain of a specific model, kind of. But I think it's also an important topic to look into this dosing of stimulation, because currently most clinics still use the 120% of the motor threshold, and it's known that the motor threshold is not, or the motor excitability is not the same in the frontal cortex. So I guess what the heart-brain coupling might offer is that it's, you really show physiological engagement of a network, and that's something very clear. So I see kind of the thumb twitch during a motor cortex stimulation could be, the heart-brain response could be the same thing, but then in the frontal cortex. So in that way, I think it has real good potential, but I think I don't have the expertise to compare it specifically to the E-field modeling.
Thank you very much. Good answer. Your thesis in general builds a really strong case for individualized TMS treatment, be it based on heart-brain coupling or also other ways to personalize the treatment. But if you take a step back, do you think that in 10 years from now on, personalized TMS will still be like the most promising technique for depression treatment, or other brain stimulation techniques, be it invasive or non-invasive, that might actually have even higher potential? And if so, does heart-brain coupling still play a role in this?
Well, it's a nice question. So I think in the broader sense, I think personalized, or at least individualized treatment wouldn't focus specifically only on RTMS, but on all the available treatments out there. So it would be amazing if we can define some easy biomarkers and combine them maybe to stratify patients to the treatment they are more likely to respond to. And if they end up with TMS, then I think heart-brain coupling is something that is really, well, has potential. We have to find out if it's really the case. But at this point, I hope that in 10 years we have developed it and seen if it can help in the localization of the TMS and maybe the dosing.
Thank you very much.
Thank you very much for the questions and answers. The opponent will now be continued by Dr. Anne Weigand. She's expert in systems neuroscience and affiliated with the Medical School Berlin in Germany. Please.
Yeah, thank you very much. And I would also like to thank you for the invitation and for the opportunity to join this special day today. And yeah, dear candidate, I can only repeat what Martin Tick already said. Really congratulations on this wonderful work. Congratulations also to your supervisors. I think that you really tackle a very important topic in this research field, because as we all know, TMS is an established treatment for depression, but still there is a lot of variability in the treatment, and some patients do not respond to the treatment. And you really introduced a very fascinating technique to personalize the treatment in depression, which is, as you've mentioned before, really feasible and can be implemented in daily clinic business. And as you've mentioned before, I think it's a true game changer, actually. I really enjoyed reading your thesis and how your studies also build up on each other. And I have actually a question about chapter 4, where you showed nicely that those patients or subjects that had actually negative correlation to the subgeneral cingulate were the ones that had really the strongest HBC, the heart-brain coupling effect. But you did also find some subjects where this connection was actually positively correlated. And how would you discuss that? How would you see that? And could maybe other regions also be involved here?
Highly esteemed opponent, thank you very much for your kind words and question. Indeed, so I think in our results in the end, 12 out of 14 subjects showed strongest heart-brain coupling at a negative or anti-correlated site to the subgeneral. And for 2 out of the 14, it was a positively correlated site. We included a bit later when we've started the study, we also included the neutral target because we realized that positive correlation is still some correlation between the areas. So we weren't exactly sure how this would, how that would work out. And I think in a recent study, they actually focused on stimulation of the positively correlated areas to the subgeneral, and they actually found good results on the depression. So I think that sheds some light on maybe the prevailing focus on the anti-correlation to the subgeneral being the most important. I think, of course, this is one study compared to a lot of studies already being done. But I think that the effect of the anti-correlation and positive correlation might need also some more studying. And in the end, I think we want to know with the heart-brain coupling whether we engage a relevant network that is effective for the depression. And if in the end it turns out that it's sometimes a positive area, but still this is working for that individual, that would still be fine. Mm-hmm. So yeah, that's kind of my take on that.
And what do you think about parietal sites to be stimulated in the future for TMS treatment in depression? To stimulate more like parietal sites?
Parietal sites.
Yes.
Yeah. So of course in that study we also applied it parietally, and so the reason to include those areas was because there was peak anti-correlation to the subgeneral there as well. And in addition, I think there are some studies showing first promising results in depression and also other psychiatric disorders. It has less muscle tissue, so it might be more tolerable for patients. So it would be something we could consider. But in the end, at least in our heart-brain coupling study, we didn't find the same results as we did at the prefrontal sites. So at least this heart-brain network might not work the same, or this area might not be directly engaging this network. So for heart-brain coupling purposes, I'm not sure yet. But if you take into account your previous question with anti-correlation and positive correlation, in the parietal sites, I think there were about at least half of the patients who actually showed the strongest heart-brain coupling at a positive spot. So if it turns out there that there is some room, like there would be more possibility as well for the parietal areas.
Yeah, and do you think that other brain networks could also be involved, or which ones do you think could be relevant?
Yeah, at least I think the dorsal ACC is an important area that is most likely involved as well. And at least during writing of my thesis, I also came up with more the networks that might be the dorsal default mode network, the salience network. I think those networks are definitely important because they are both, for example, the insula, it's important for also introspection, and it's related to heart rate control and depression. So I think there are some more areas that could be explored.
Very nice. And maybe as an outlook, where do you see ways to further improve the personalization, maybe by adding other physiological measures in addition to the heart-brain coupling, or maybe behavioral measures, or what do you think could be a promising parameter to be included in the future?
Yeah. I think it would be nice if you could combine some, and I think mostly this autonomic functioning has some potential. So you have the heart-brain gut axis, so you could include something there, or pupil dilation, I think, is also a measure of autonomic output. You could think of inflammation markers or hormones, or I think there are some things, or blood pressure. I think I'm not sure which one has the most, is the most promising there. But I think by combining some of these measures, you have a bigger picture of what's going on.
Great, thank you very much.
Thank you.
Thank you very much. The opposition will now be continued by Professor Sonja Kotz. She is Professor for Neuropsychology and Translational Cognitive Neuroscience at the Department of Neuropsychology and Psychopharmacology at the Faculty of Psychology and Neuroscience here at Maastricht University.
Dear candidate, let me join my colleagues in congratulating you not only for an excellent, highly enjoyable reading experience of your thesis, but also this incredibly professional presentation today. I had lots and lots of questions, but time limits us to one chapter. At least that's what I chose. And my focus is on chapter 3, and I have questions regarding methodological aspects, technical and practical challenges, and if time permits, an unexplored variable. So you acknowledge in study 1A that pain could be a confounder in the results that you actually have. I wonder at the same time if pain is stronger in the active TMS than in the sham. This could lead to additional factors like stress, or stress in the first place that someone is going to zap me somewhere. So I'm wondering how you could explain or exclude the possibility that it's not pain-induced sympathetic alteration, but really truly the mediation of heart rate deceleration.
Highly esteemed opponent, thank you for your kind words and the question, which is a very important one, especially in TMS research, because the TMS can feel uncomfortable and that can also affect heart rate. So in chapter 3, we included, I think, study 1, an extra study to see if we could already find some proof or reasons to think it is pain or it's not pain. But in that chapter, the 4 reasons I think for believing it's at least also partly the TMS inducing the effect specifically was that it's decelerating heart rates, which you would not expect during a painful experience. So mostly when you have pain, this activates your sympathetic nervous system, stress, and that would, accelerate your heart rate. And also because the heart-brain coupling is over a longer time, you would expect, and it actually increases dose, you would expect some linear dose response then on pain, because the intensity goes up. So the end would, I would expect at least would be the most painful. But we didn't find, per individual it varied, but you also saw an inverted U-curve response, for example. And it was site-specific, so even we stimulated 2 different areas of the DLPFC very close to each other, sometimes only 1 centimeter apart, and we saw clear differences in the reaction on the heart-brain coupling. So that showed us that there is at least some, that can be only a pain. But to add with later results as well. We included pain measures in chapter 4, and we didn't find any correlation there. And interestingly, there's actually, very recently, there was also 2 patients with OCD who were stimulated intracranially at the subgenual ACC with DBS. And that also induced the heart-brain coupling, which shows that it's really a specific effect on the brain as well. So I think those arguments show us that it's definitely not only sensation effects.
Okay, fantastic. I'm just wondering, in this context too, very often depression is very tightly bound to anxiety or anxiety disorders. And how far do you think this could be an additional level of consideration in this dynamic? Specifically, I'm going towards stress again. I may be incredibly anxious to start out with such a hopefully a helpful measure.
Yeah, so you mean really in the clinic,
Yes.
if you are with your patient
Yes.
and they suffer also from anxiety. That's a very important one. So I think communication with the patient and also making sure that clinicians working with the heart-brain coupling know why and how it works is very important. So I think the psychoeducation, I think is called, part before you start with RTMS is really helpful there. So when you explain a lot what someone might experience, this helps. I do acknowledge that the heart-brain coupling assessment is more or less tolerable than a normal TMS session because it's because the increasing intensity can be quite the end can feel quite intense. But we did notice that there were almost no patients that weren't able to do the heart-brain coupling assessment. So explaining it well to the patient and making sure they know that they can feel maybe the eye twitch or feel some pain at the stimulation site, that helps a lot.
Okay, then let me move on to within the same chapter, figure 6. So there you talk about the frontal excitability threshold determination, and I was wondering what you consider to be a sweet spot of intensity, and that relates to the kind of question that the inverted U-dose response suggests overstimulation risk. And the thresholds vary widely. So where do we find ourselves here?
So in figure 6, you see the I think 10 different individuals that were stimulated, and we looked kind of where the heart-brain coupling peak arose. So like in this study, at least, we had our first thoughts about. Does this peak of heart-brain coupling show us the best engagement of the network? Because then you would want to find the highest or strongest heart-brain coupling and at which intensity, because this is a ramp up, so it ends in the highest intensity. And then if you see it already early, we want to see it, I think, 2 intensities in a row. Right. We choose that stimulation intensity.
Okay.
But of course, this is still, we haven't tried this in clinic yet. This is hypothetical. I would really want to investigate this in the future to see if it can actually help also, if it changes the outcome in patients with depression.
Right.
But the optimal stimulation site is the peak with the highest heart-brain coupling.
Super. Maybe one last question, and that relates to the site specificity. In study 2, you found no group level differences. But individual best sites varied. So what neuroanatomical factors do you think drive this variability?
So for this study, we of course we want to find individual differences. That's kind of the whole idea of the heart-brain coupling. And that's also why we felt it was difficult to explain to reviewers as well, that you don't find a group level difference, because if for the one individual, well, we had 4 spots actually that we stimulated, and they all varied. So then, because your question was on neuroanatomical.
Yeah, whether you can consider any neuroanatomical factors that may underlie this.
Yeah, so I think the neuroanatomical answer I would have here is that for the one individual, you would engage the area connected to this, well, heart-brain network, and thereby hopefully the depression network, in, for example, the 5 centimeter rule target on the right, while for someone else that would be the B method on the left. And that, well, would be great for an individual that would improve treatment, and that would not show any, well, group level difference.
Okay, thank you very much.
Thank you.
Thank you very much. Then the opposition is continued by Professor Theresa Schumann, Professor for Clinical Applications of Non-Invasive Brain Stimulation at the Department of Cognitive Neuroscience of the Faculty of Psychology and Neuroscience at Maastricht University.
Thank you, Pro-Rector. Dear candidate, dear Eva, I also want to join in to the congratulations. I really enjoyed reading your thesis, and I found it quite impressive how you actually combine methodological development with clinical relevance. It was really nice to see how you also did this translation from basic research to clinical applications, and I also want to congratulate your supervisory team for guiding you in this journey. Sonia also wants to congratulate the supervisory team. I want to ask a bit of a technical question to begin with. In chapter 3 and 4, you actually describe the DASH protocol as using 5 seconds of stimulation followed by an 11-second intertrial interval, resulting in a 16-second cycle. And I got very confused because I always teach the DASH protocol as a 15 seconds protocol. And I dove into the literature, and you cite Carpenter as well, and Carpenter also says, well, no, it's actually 4 seconds on, 11 seconds off. So could you clarify this deviation, and could you tell me whether this choice was deliberate? And if so, how you think this affects the interpretation of your heart-brain coupling findings at 0.0625 Hertz?
Highly esteemed opponent, thank you for your kind words and your question. And that's definitely true. So the DASH protocol described by Carpenter et al. Is 4 seconds and 11 seconds off, or at least that's the shortest intertrain interval. So all the way at the start, when Martijn, Arns, and I were discussing how we could identify kind of the protocol to use, but also to make sure it has an impact, because we saw difference between ITBS and 10 Hertz. ITBS was more able to induce strong heart rate decelerations, 10 Hertz less so, and because a 26 seconds of intertrain interval would, wouldn't maybe induce the strong heart rate decelerations. So I dove into all the safety parameters of TMS, and there are some studies on that, in which 10 Hertz stimulation can be applied safely for 5 seconds in a row. That's the longest duration that is described there. And then the shortest intertrain interval is the one described by Carpenter et al., which is 11 seconds. And we combined these two, which we indeed call the DASH protocol. So I'm not sure if that's fraud in that way. But we do describe always clearly that we use the 5 seconds and 11 seconds. But because of that choice, we have been using that all out. I do think it's it does make sure you have enough 5 seconds of stimulation can really induce the effect on the heart rate. So I think for now we stick with that protocol.
Okay, that's clear. Maybe I would recommend not calling it the DASH protocol then. Yeah. And how would you use this then? Would you actually do 75 trains eventually if you use this clinically, or would you reduce them then because you have 5 seconds?
7.
Well, the normal DASH one has 75 trains of 4 seconds, which results in 3,000 pulses. Would you then also go for 3,000 pulses, or would you actually increase the amount of pulses?
So we only use the DASH protocol in terms of the heart-brain coupling assessment.
Yeah.
And there we only stimulate for 4 minutes, 15 trains in total, during every stimulation site. So I think you only reach there 75 trains? No.
No, but you would want to translate this to clinical use, right? So how would you adapt the protocol then? Would you go for 3,000 pulses, or would you go for 75 trains?
So I would not exceed the amount of pulses, but I think in clinical terms, also at Neurowave we treat with 4 seconds of stimulation. Okay. So this described method is really focusing on this heart-brain coupling assessment, which is actually no treatment, but only target localization.
Okay, good, thank you. Then I have a question about your chapter 2, because in your chapter 2 you actually stratify your analyses by biological sex, and you cite that there are known differences in the prevalence and characteristics of sleep disorders. Could you tell me why you actually chose full stratification over, for instance, testing a sex by sleep disorder interaction, a unified model? So I find this surprising that you separate men and women in the analyses. And do you think this stratification approach might have actually limited the statistical power, especially in your replication analysis or in your replication sample?
So I think there are really biologically different, like in the brain, there are differences between men and women that are shown specifically for sleep disorders. But I think I also made a reference to that in the chapter. And as you still ask the question, I guess I need to come up with a better answer. But we did decided on that even before we did the study. So I guess it actually, if we would be able to combine the groups, and that would definitely make more power, because then we have one big group of patients. But I think we also split them up for, oh no, it was only on biological sex.
Yes.
Yeah. Yeah, that would be that would maybe be a nice thing to investigate. But at least at that point, we did have some references that showed us that it might be well, a good idea. Also, I think sleep disorders are more often common in women, and also depression is more often in women.
So should we do all these analyses when all the depression data that we analyze, we should also stratify by gender then? Is that what you would recommend?
Yeah, because we didn't do that, so that's, yeah, a good question.
Okay, good. Glad. Then I have another question about chapter 2, where you actually describe a protocol where participants transition to a bilateral stimulation after 10 to 15 sessions. It wasn't entirely clear to me how many sessions these patients got in total. And considering that new studies actually show that ideally patients receive 36 or more sessions, do you think the early switch to bilateral stimulation or the limited number of sessions could have influenced your finding of the predictive value of sleep disorders?
So indeed, our previous way of working, so this is based on a retrospective data set of, I think, at least 200 patients that already received treatment. And we always worked based on the fact that it seemed to be predictive if after 10 sessions someone would have a 40% response rate, then someone would probably respond to treatment, and otherwise it would be wise to maybe stimulate bilaterally. So all patients received bilateral stimulation after session 10 if they didn't reach the 40% response rate yet. And at that time, at least, because this is already 2019, 2018, it wasn't clear yet that 36 sessions was kind of a minimum, or at least something thought to be the optimal dose. And I have to be honest that we almost never stimulate for 36 sessions. Mostly we see the effect faster. So I think in the data we had an average of 21 sessions in our patients. So that's definitely less. Whether it affects the predictive value of sleep disorders. I don't think so, because well, at least in the whole group, we had this outcome measure, and because it didn't predict the outcome, it shows us that maybe people already, like their sleep also improved during treatment, or there was some other reason why the sleep disorders had no predictive value. But I think if you add 10 more sessions, well, I don't know what I would expect, but maybe you have an idea on what could happen there to make it more likely to have could be a responsive biomarker.
Mm-hmm. I don't know either. I think it's a scientific question that we should see. But I wonder, if I may, I wonder, because you have your own clinic, and now we know that we should actually, that some people actually don't show response at all in the first 10, 15, 20 sessions. So now that you have the new knowledge, would you now not switch that quickly anymore, but say, well, I continue and then switch much later? Or?
Yeah, so I think, well, at least there's even a question about whether bilateral stimulation really adds up. So we now completely moved to a situation where we stimulate at least for 25 sessions at one location. We now always optimize the stimulation site based on the heart-brain coupling. So we want to really have a clear view on what happens after 25 sessions there. So that's what we do.
Very good. May I have another one? Or yes? Okay, perfect. We'll just continue. In chapter 5, which also links to what you just said, you try to stratify patients to one of 4 predetermined DLPFC TMS targets-based sites. And you look where heart-brain coupling is strongest. But if you actually believe that heart-brain coupling truly provides a physiological marker of network engagement, why restrict the search to a few predefined spots? So why don't you use a more continuous grid-based or a neuronavigated search, probably random sampling between prefrontal areas, to actually have a better chance in finding patient's optimal site?
I'm really happy you asked the question, because of course that's kind of the limitation we work with now. We wanted to investigate heart-brain coupling as soon as possible, and also try to find a way to get it to the patient as soon as possible. And by using, well, evidence-based predefined targets, we're able to define within subject at least the better one of those 4 sites.
You can wrap up your answer.
But I'm hopeful that we would be able to move toward a situation where we indeed stimulate a grid, more areas on the brain, and just to find the individual site where you see the strongest heart-brain coupling. So definitely.
Thank you very much. I'll give the word back to the pro-rector.
Thank you. Eva Dijkstra, the time for defending your thesis has passed. The decree committee will now withdraw to discuss the quality of your thesis and your defense. I request that you and your company await the results of our deliberation and our return in the room.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Long road to the south side. 7 miles in my rearview mirror, I know what it felt like. My goals only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. On the line, I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile. Long road to the south side, 7 miles in my rearview mirror. I know what it felt like. My goals only getting clearer. East side to the west side, no place like home. If it's questions that you've got, go the extra mile and not. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. Get the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. And even though these nights seem long, I know that I am never on my own. Know you've won the battle once you've grown. South side, 10 miles in my rearview mirror. I know what it felt like. My goals only getting clearer. East side to the west side, no place like home. If it's questions that you've got, go the extra mile and not. Long road to the south side, 10 miles in my rearview mirror. I know what it felt like. My goals only getting clearer. East side to the west side, no place like home. If it's questions that you've got, go the extra mile and not. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile.
bij Janne gaan staan zo. Nee, zo meteen. Okay.
Eva Dijkstra, the decree committee here present has assessed the quality of your thesis and your defense. In view of its positive verdict and taking into account your previous qualifications, the decree committee has decided to grant you the degree of doctor. Professor Sack is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
Please, all right.
So English, yeah? Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I promise.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Eva Sophia Anna Dijkstra, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with a degree certificate signed by the rector, the secretary, and the other members of the committee and affixed with the official seal of the university. Yeah, gefeliciteerd, congratulations, Dr. Dijkstra, Eva. I only will say a few words before I give the word to Martijn to give the laudatio. I would like to thank you very much for working together with me and us for the last years. It was really very enjoyable to work with you. And I also want to thank Martijn and Hanneke for the great cooperation. I stopped counting how many PhDs we now did together, but it's quite a bunch, and this cooperation with Brainklings is really wonderful for us. So thank you again, Martijn and Hanneke, for this cooperation. And only a few words. I mean, we know each other for a long time now already, and I said this to you also in Amsterdam when we met. But I'm really truly impressed how, even on a day like this, where I'm sure you must be a bit stressed or nervous, you managed to be 100% yourself, 100% Eva. People actually commented, and they don't know you, that they felt this positive energy that fills the entire room when you speak and when you talk about your work. Mm-hmm. And you also seem to enjoy yourself in the moment, which is a great talent that you have. Your presentation was absolutely fantastic. Some people mentioned it was probably the best presentation they saw in such a context. It was mentioned that the thesis was one of the best theses they ever read. These are quotes from the discussion we just had in the room. So people are truly impressed by your work and especially by your personality. So thank you very much, Eva, and I'm really hoping that we stay in contact for many more years to come. And now I give the word to Martijn for the laudatio. Thank you.
Thank you.
Nou, ik mag het eindelijk zeggen, wel edel, zeer geleerde dokter Eva Dijkstra.
Yes.
Beste Eva, ik wil je hierbij van harte feliciteren met het behalen van deze titel. Daarnaast wil ik ook je man Daan, je familie, je vrienden van harte feliciteren met deze mijlpaal. In 2019 leerde ik je kennen tijdens de TMS-cursus. Volgens mij was dat samen met je moeder inderdaad ook.
Zeker.
Dat herinner ik me nu inderdaad. En daar, ja, op basis daarvan was natuurlijk je interesse gewekt in het brain stimulation field. Dus het brain stimulation virus is toen bij je aangekomen. En je paste ook al TMS toe in je eigen praktijk bij Neurowave. Initieel had je plannen om dit te combineren met onderzoek aan het AMC, maar al snel voerden we verder gesprekken of het niet fijner was om toch toegepaster onderzoek te doen. Waarbij je dus ook de data verzameld in je eigen praktijk kon gebruiken bij Brain Clinics. En gelukkig zijn we die samenwerking aangegaan en we zien vandaag daarvan het resultaat gelukkig. Als ambitieuze startende ondernemer van Neurowave was het aangaan van een PhD-project een behoorlijke uitdaging die je met verve vervuld hebt. Echter, het bleef niet alleen bij deze uitdaging, want vanaf het begin al speelde je een rol bij de Hersenstimulatiestichting, waar je nu onder andere voorzitter bent van de klinische commissie. En daarnaast in 2004 werd je ook nog directeur van de Hoofdlijn, nog een andere GGZ-instelling. Kortom, een uitdaging kun je prima aan wat dat betreft. En om het plaatje helemaal compleet te maken, besloot je ook om zo ongeveer tegelijkertijd met het afronden van je PhD, om met Daan in het huwelijksbootje te stappen, wat bekroond werd met een huwelijksreis, heel toepasselijk aansluitend op het Brain Stimulation Congres in Japan. Dus de Brain Stimulation was nooit ver weg, zeg maar, zelfs niet in de huwelijksreis. Ik heb je leren kennen als een enthousiaste, ambitieuze en hardwerkende onderzoeker en een vrolijke noot in het team. Jouw aanwezigheid creëerde altijd een gezellige sfeer, wat ook merkbaar was op de vele internationale congressen waar we met het team geweest zijn. Van Charleston naar Zagreb, naar Lissabon en nog vele andere. Befaamd werden daarmee ook de Brain Clinics etentjes die eigenlijk spontaan georganiseerd werden. Iedereen werd bij elkaar geroepen en we gingen eten en daar speelde je een belangrijke rol in. Maar met name ook het voorbeeld wat ik wil memoreren in Zagreb, waar jij en een aantal andere collega's eigenlijk het stijve feestje van een aantal wetenschappers probeerden wat op te schudden. En uiteindelijk alle stijve wetenschappers aan het dansen hebben gekregen door de stoelen aan de kant te schuiven en de DJ te vragen voor goh, iets andere muziek tot voor mij Metallica aan toe. We hebben er alles voorbij horen komen. En vele collega's memoreren die avond nog steeds als een van de avonden waar het Brain Clinics dansfeest mede door jou geïnitieerd werd. Dus dat schetst denk ik ook wel een beetje van jouw rol, wat mensen vandaag gezien hebben, maar ook hoe je op congressen daarin bent. Ook tijdens de lunches had je altijd interessante anekdotes. En een interessante die ons allemaal is bijgebleven is de EpiPen. En dan weet je denk ik wel welke ik bedoel. Er was een patiënt en die had een EpiPen bij zich en die moest gebruikt worden. En uiteindelijk bleek die EpiPen een oefen- of nep-EpiPen te zijn. Dat was wel een beetje een bizar verhaal. Wij maken ook veel mee, maar jij komt altijd met dat soort anekdotes. En dan denk ik van, heb ik dat nooit meegemaakt. Het hoogtepunt van je promotieonderzoek was natuurlijk de periode die jij en Daan hebben doorgebracht in Boston bij de groep van Chance en Dicky. Wat bijzonder was dat deze groep spontaan ook aanboden om, dat heart-brain koppeling is natuurlijk heel erg leuk, maar laten we dat gaan valideren. En dat aanbod hebben we aangenomen en godzijdank ben je daar naartoe gegaan. Het was een hele leuke tijd natuurlijk. Maar bovenal hebben we inderdaad kunnen aantonen dat dat gekke idee wat we hadden, dat het klopte. Ja. En dat met simpelweg een app en een ademhaal of een hartslagband te gebruiken, we eigenlijk met bijna 90% betrouwbaarheid het juiste netwerk konden identificeren. En ook met publicatie in een vooraanstaand tijdschrift van Nature Mental Health. Je hebt bijna 4 jaar onderdeel uitgemaakt van de Brain Clinics onderzoeksteam. In het bijzonder de Heart Brain Group, samen met Lauren, René en Hanneke. Ik neem aan dat we vandaag nog zeker getuigen gaan worden van het door jullie op wetenschappelijk verantwoorde wijze onderbouwde heart-brain koppelingdansje en liedje. Maar misschien niet nu. Helaas heeft Martin was supposed to ask that question if you could demonstrate it, but after some pre-discussion we decided to maybe wait for that later.
Thank you.
But we still hope to see the heart-brain coupling dance. Eva, ik heb met heel veel plezier met je samengewerkt en wens je het allerbeste toe in de rest van je carrière. Van harte gefeliciteerd.
Dank je wel.
Dear Dr. Dijkstra, also on behalf of Maastricht University, I want to congratulate you to your achievement. And now a few things for the next steps. So we will have in the refter a little bit to eat and drink. And please follow just, some of you might know the way, just go there. We will stay here for photos and come a bit later. And we also, with the family, go to the staircase soon to, after doing photos here, to do some more photos. And then we join you in the refter. With that, I want to close this academic ceremony.
Nou, ik heb zo vaak gevisualiseerd dat dit moment was, zeg maar. Wow, het is gewoon gelukt. Oh nee, dat hoeft helemaal niet. Nee.